Hello, this is Raf Alvarado and welcome to Exploratory Text Analytics. In this video, we're going to look at entropy measures. So you've looked at the concept of entropy, seeing how it is both philosophically and mathematically pretty important. I consider it to be the foundation of text analytics, even though it's not often recognized to be such. But you'll often see it used in lots of different places to evaluate performance, to evaluate distance, and so forth. And so what I'm going to do right now is just give you a quick overview of some of the more basic measures that you're going to find without diving too deeply into the math, just kind of showing them to you. This is more so you can just have the vocabulary in your head so that you can refer back to these when you see them pop up. Okay, so the first one we want to look at is, let me see if I can get this to, there you go, is divergence. Divergence is a measure of, it's not technically a measure of distance because it's not symmetric, but it's used in the context of measuring distances, and we're going to look at distances more in detail when we look at vector spaces later. But there's an important measure called KL divergence that you should know about and understand its notation. You'll see that listed here. D standing for divergence, the subscript KL standing for Kullback-Leibler. And then PQ. So these are two vectors, and the double bar just stands for divergence. Instead of putting a comma there, there's a double bar there. So the way you calculate that is pretty much the same formula that you use for entropy, except that instead of just having in the log element of the formula, you have a fraction, a ratio, where you throw in another distribution as the denominator. That is an interesting measure, and it produces, again, a measure that is not symmetric. In other words, if you take the divergence of P and Q, it's going to be different than the divergence of Q and P. And so there is a way to normalize that. The equation below, it's called Jensen-Shannon divergence, where you basically add the two directions of divergence and divide by 2. This is often called the relative entropy between two sets of events, and it's related to things like information gain and so forth. And it's an extremely important concept in this field, and it's helpful to understand how it derives primarily from Shannon's theory of communication and the theory of entropy derived therein. Okay, so that's divergence. Another concept is one called cross entropy. It's where you compare the, it's a way to compare the difference between two distributions that refer to the same set of events, such as a language model and the actual distribution that you find in empirically. The Q is typically the model and P is typically the actual distribution. Oftentimes this is used to compare trained and test distributions, and note that it can be expressed in terms of divergence. So you've got the entropy plus the divergence is essentially the cross entropy. Another concept is that of perplexity. Perplexity is, excuse the pun, it's perplexing in the sense that it's not clear why it is used. And we'll see a slide about that in a second. It's really just the same thing as entropy. It's just a way of expressing entropy. It's often used to express cross entropy, so you'll take the perplexity. The perplexity is oftentimes 2 to the cross entropy of something. But the basic formula is just you take the entropy and you exponentize it. This is often used as a way to measure the performance of language models. But very often, because we don't know the actual model that we're working with, we assume maximum entropy. And so we use just the inverse probability of the test set as our first px, and which is just the normalized, just the inverse of the number of words in the distribution. Anyway, in the equation right there, the second one, the b, is often typically set to 2. I'm going to show you a quick quote here from Manning and Schutz, which is kind of funny, which refers to probably the motivation for using perplexity as a measure. Here he says, or they say, "We suspect that speech recognition people prefer to report the larger non-logarithmic numbers given by perplexity mainly because it is much easier to impress finding bodies by saying that we've managed to reduce perplexity from 950 to only 540, than by saying we've reduced the cross entropy from 9.9 to 9.1 bits. However, perplexity does also have an intuitive reading. A perplexity of k means that you are as surprised on average as you would have been if you had had to guess between k equiprobable choices at each step. So he concedes that there is a value to it. But the point is that perplexity is just entropy exponentized. So those are your really basic sort of foundational measures that you're going to see throughout later in this course, but also just in general in this field. There are also some related concepts related to entropy, which are really important. One is joint entropy. There's conditional entropy. I actually already mentioned relative information and divergence. There's mutual information, and again, I've already mentioned cross entropy and perplexity. These are all concepts that are used throughout the field and which really establish the importance of entropy as a concept in getting work done in this field.